Thank you so much for coming. Sorry about this room layout. Obviously, everyone's sitting on the edges, and I'm a bit of a wanderer, so I'm left-handed. I apologize to you folks if I end up being biased to that side, but I suspect we'll see how it turns out. So I'm going to talk today about Kubernetes. We'll go a little bit deeper than some of the kind of intro topics that you may have already seen. So my name is Shahid Iqbal. I'm a freelance hands-on consultant working in kind of .NET, Azure, and Kubernetes projects. I'm a developer. I've been for more than 10 years, and I'm also a Microsoft MVP. I'm based in the UK, although I work globally. I was based out here a few years ago, actually, and I really enjoyed my time, so I'm really pleased to be back speaking here as well. And I run a meetup in the UK, and I always take an opportunity when I'm speaking to a group of people to encourage them to get into speaking. I did this about 2 years ago, and I've loved it ever since. So start with a little lightning talk if you want. Just contact your local meetups. There's a really active meetup scene over here as well. Highly encourage it. Main reason for these slides really are my contact details. We'll see how we get on with time for questions. But if I don't get to your questions today, grab me. I'm around for the rest of the conference. But if not, feel free to ping me on Twitter, LinkedIn, email, wherever you want. So what are we going to cover today? Broadly speaking, we're going to talk about scheduling. We'll talk a little bit about admission controllers. And I'll touch on how we can extend Kubernetes, some of the options. Then we'll do a little bit of a shift, and I'll talk a little bit about scaling. And in particular, I want to cover two topics, one around virtual node and one around KEDA or KEDA. As always with cloud-native projects, we always argue about how we pronounce things. There's another one. And hopefully, I'll have some demos for you along the way. So what I'm not going to cover the fundamentals of Kubernetes. My assumption is that everyone in this room has a good grasp of the basics, as the synopsis kind of said. So you know what pods are, you know deployments are, you know services, et cetera, et cetera. I'm also not going to deep dive into how we create custom resources and operators. Again, that's quite a deep topic in itself and is actually probably best suited for a workshop. Final disclaimer is that the definition of advanced is very subjective. My idea of advanced may not match your idea of advanced. So if having seen that list of topics, if you think you know those topics really well, please feel free to find another session. I won't be offended at all. Otherwise, stick with me. Even if there's something you know initially, hopefully there'll be something else that you haven't seen before. Before I start, it'd be useful just to get a read of the room. So how many people here are developers working with Kubernetes? OK, I would say probably about half. Operators, people who are responsible for operating Kubernetes. You can be one. You can be both. Really, nobody here is responsible for operating the clusters. Wow. OK. So what do the other half of the room do? Security? Architects? OK, cool. Anybody brand new to Kubernetes? OK. I don't know if you heard my disclaimer at the start, but great. Just want to make sure. So pod scheduling. When we look at the control plane, it's comprised of a number of components. We have the API server. We have the scheduler, controller manager, and cloud controller manager, and etcd. And when I do an intro talk, I basically say the scheduler's job is to find some way to run your containers, or pods. Today, we'll dive a little bit deeper into what that actually means. At a high level, when we talk about scheduling pods, what does the scheduler actually do? Essentially, when you create a pod, the scheduler detects that there's no node assigned to that pod, and it simply assigns a node. Now, simply is misleading here. The scheduler has a very complex algorithm that it chooses a number of parameters to decide where to schedule your pods. But most people who come to Kubernetes, certainly in the initial phases, don't really need to know anything more. They just need to know the scheduler does its job, and generally does a pretty good job of that. But sometimes you need a little bit more control. Why do you need this control? Well, you might have a cluster that's got some specialized hardware or software running in it. And you want to make sure that workloads are using that particular hardware or software. Similarly, you may have multi-tenanted teams. You may need to allocate certain resources to certain teams. You may have regulatory requirements that say certain workloads must run on certain machines or with certain software on those machines. Alternatively, this may be an application architecture issue. You may want to ensure that certain components within your app architecture are located together, or probably more commonly actually, you'll want certain components in your architecture to not be located together. We'll talk a little bit more about that in a second. When we have a think about the options we have for scheduling, we've got a number of these. And what we'll do is we'll talk about each of these one by one. So node selector. This is the most basic approach for telling the scheduler where you want your pods to run. You simply add a node selector element into your pod spec. You give it a label, a key value pair, and the scheduler will find a node that has that label on it and schedule the pod there. Now, there are a number of labels already added to nodes. So this example here, this is a AKS node. And we can see we've got some labels around the VM type here, the region it's in, the zone it's in, and something to do with the storage. So these are added in, and we could specifically say, if we wanted our workloads to be run on a particular VM, we would target this label here. Now, if that label isn't sufficient, you can actually add your own custom labels. And you simply do that by doing kube control. And actually, I should point out, in my demos and in my screenshots, whenever you see K, that's me. I've aliased kube control to K. Because one, we don't have to argue about whether it's kube control or kube cuddle or kube control. And two, I don't want to type kube control every time. So K is just much easier. So if there's nothing else you take away today, just alias kube control to K. And then hopefully that's enough. So what I do kube control label node, give it the name of the node, and then I give it my key value pair. Now label the node. Node selector has some issues. It's matching basically on an exact match on the key value pair. Another problem in node selectors is if you specify a node selector in your pod spec and there isn't a node with a matching label, your pod won't get scheduled. It'll be sitting pending forever. So with this in mind, this is where node affinity and anti-affinity comes in. So similar to node selector, they allow you pods to decide which node to run on. But now they have a little bit more flexibility. So rather than matching on a precise label, you can now have some conditions. So you can specify things like it's in a list of values, it's greater than, less than, whatever. Crucially, you can also now specify how demanding you are about the presence of that label. So how do we do this? When we talk about specifying the demand, we use a rather wordy parameter called required during scheduling, ignored during execution. What this is saying is this label must exist on the node. Otherwise, if it doesn't, don't schedule it. So this is essentially the same behavior as a node selector. But now we have this option of having a soft requirement. So now we're telling the scheduler that please use a node with this particular label, matching those conditions. But if you don't find one, don't worry, run it somewhere else. Now, if you're looking at this, you're thinking, well, what's all of this ignored during execution? That's pretty redundant. Well, there is another option. It's not been implemented. And this option says required during scheduling, required during execution. So the required during scheduling is in the scheduling phase, whereas during execution suggests that when a pod is already running, you may want to take an effect. Now, this has not been implemented, and it probably won't be, because there's other ways of doing this now, which we'll touch on. So how do we do node affinity? Now in our pod spec, we have the affinity, and here's that required during scheduling or during execution. And then here's our selector. So now this time we're saying, for example, we want the instance type to be a particular instance type. Here, even though I've said an in, and this could be a list, I've just specified the one instance type. So here I'm asking the scheduler to use a particular VM type in my cluster to run my workloads. This is the hard requirement. On the software requirement, the preferred, we have this additional parameter called wait. And what the wait is doing is telling the scheduler that, all right, there may not be a node with the requisite labels on it, but how strongly do I want you to prefer one over the other? So this is just like a waiting to make it use a particular label. So node selectors, they solve all the problems. No, not quite. So one of the problems with node selectors and affinity is they don't prevent certain nodes from having workloads deployed to them. The two options, the node selectors and affinity, are used by the pods to say which node I want to go on, but nodes at the moment have no say in the matter. If you wanted to prevent a particular node from being deployed to, you would have to update every deployment in your cluster and add a node selector or add a node anti-affinity. This is where taints and tolerations come in. So taints and tolerations, taints allow a node to repel pods. So this says, do not deploy anything onto me unless that pod tolerates this taint. These taints are comprised of 3 parameters, a key, a value, and now additionally this effect parameter. And the effect can be no schedule, prefer no schedule, and no execute. So this is where taints and tolerations differ from the selectors and affinity I've talked about so far, because existing running pods can be evicted from a node if you add a taint to a node and you don't tolerate it. And Kubernetes actually adds some of these taints to nodes in certain conditions. So for example, when a node is running out of memory, Kubernetes will taint it to say it's running out of memory. Same with disk space and several other issues. So how do we taint a node? Not too difficult. Kube control taint node, give it the name of the node, and now we're doing the key, the value, and additionally this effect, so no schedule. If I take a look at a deployment without tolerating it, so this is a 3-node cluster, and I haven't put any kind of toleration in my pods, we can see that I'm running two of those are running on one node, and one is running on one, and nothing's running on node 0, which you normally would expect. If I now add a toleration to this pod spec, so this time I'm saying I'm tolerating that particular value. This toleration seconds is interesting, because what toleration seconds does is it says if a taint is added to a node, I will wait that amount of seconds before I kick off this pod. What that lets you do is, let's say you have a transient issue, a transient memory issue, for example. With the toleration there, it means that the pod won't get kicked off immediately. It'll wait for that amount of time. If the issue resolves itself, then it won't get kicked off. Once I've added that toleration, when I schedule again, so I've redeployed this, and you can see now I'm getting what I would have expected, which is 1 deployment per node, which is the classic way it usually would default to. I mean, there's lots of other reasons why that wouldn't happen, but by default, that's usually what you get. So let's quickly summarize taints versus node affinity, because it can be a little bit confusing. So node affinity, any pod can be scheduled unless the pod explicitly says it shouldn't go on a node. So this is anti-affinity. The node has no say in the matter whatsoever. Whereas taints allow nodes to repel all pods unless they explicitly tolerate the taint. And as I said, the other key difference is existing running pods can also be kicked off, evicted. As always with these things, there are nuances and there are lots of subtle details. If you're looking into this, I'd recommend having a look at the docs, because there's some new things coming in this area as well, actually. And as I said, the taints, they prevent kind of casual scheduling onto certain nodes. And these nodes may be things that have limited, expensive resources. A classic example might be a server with GPUs on it. You don't want anything just running on that GPU server. You only want those workloads that need to use the GPU. And we'll see how these chains come into effect much later on when I'm talking about virtual nodes. So far, we've been talking about pods being attracted to nodes. There's another scheduling influence we can have, which is inter-pod affinity. This is deciding where to run a pod based on what else is running on that particular node. Okay? So this allows you to do things like ensure that certain components always run alongside each other. So for example, you might have a cache component and a web component, and you want to ensure that they always live on the same node. As I said earlier, more commonly, you want to ensure that certain components don't run together. So for example, you may want to ensure that the multiple replicas of your application are spread across zones. And this way, if you lose a zone, if you lose a node, you don't have any downtime. So Pod Affinity has similar constructs for indicating the strictness. So I won't label that point. You have this additional parameter called Topology Key. And the Topology Key is a little bit confusing, so hopefully we'll clarify as we go along. But this references a node label. And it says what level, and I'm using the air quotes very deliberately here, what level of the infrastructure do I use as a separation? And this could be something like host name, this could be fault domain, this could be availability zone. Let's try and make this a little bit clearer. So here's my cluster. I've got 4 nodes in there. If I look at the labels for host name, I have node 1, node 2, node 3, node 4. When the topology key is host name, it's going to treat each one of these as separate nodes. Ignore the yellow color. That shouldn't be there, the orange color. So it's going to treat each one of these nodes as a different zone, if you like, and it will spread the deployments across any one of these. If I chose the zone, and this could be an existing label or custom label I've added, now that topology key will mean it'll treat the cluster as if it's 2 blocks of servers, and we'll pick one of those 2 servers to deploy to. Let's try and let's have a quick look at what the Pod Affinity looks like. Again, it's not dissimilar to what you've seen already. This time it's a Pod Affinity, same match expressions we've seen before, and here's that topology key. So this is just a label from your node. So let's take an example of this. So I've got an application here which has got a web and a cache component. I've got 4 replicas, and I want to ensure that these are spread out evenly across my cluster, but I want one of each on each node. Now, as I said, the scheduler may do this anyway, but you want to ensure it does it. So what we do is we set Pod Affinity for the cache. So this is the web. This is the Pod Spec for the web. I've pseudocode, if you like. And what I'm saying here is I want the cache, I want my web component to have affinity with the cache component. And here I'm saying it's preferred because the cache component may not be deployed yet. So if I set that as a hard requirement, I may deadlock myself. I may have a dependency where I have to deploy one before the other. And because I'm using the topology key of hostname, and I've got 4 instances, it's going to spread those pods across the 4 instances. Now, if we take a look at the pod spec for the cache, this time we have Pod Affinity for the web. And again, we've got preferred because we just don't know which order we may deploy in. We have Pod Anti-Affinity to itself, so it's going to repel itself. And again, we're using the hostname as the topology key. So now we get that behavior. We get one of each on each of the nodes. We take an example now with the zones. So here I've got a cache and a web. And in this example, I don't care if they run together or not. I just want to make sure that each one is in an independent zone, because these zones are availability zones, if you like. So now I have, as we saw before, Pod Affinity, Anti-Affinity. The key thing now is the topology key is the zone. So look in the zone label here. So now it will pick one of these 2 nodes. Incidentally, I can combine other selectors with this, so I can use this plus other selectors to influence which one within the zone. As you can see, it gets quite complicated if you really want to. But essentially, it's going to ensure that there's one component in each of the two zones. And then similarly for the cache, it's going to do the same. Again, we're using the topology key of zone. And in this animation, I've put them together, but it doesn't necessarily mean they would go together unless I added, no, sorry, actually they would because of the affinity, but yeah. Okay. Let's very quickly touch on the pod spec. It's a lot of YAML, which I'm sure by the end of today, nobody really cares about. When you're going to work on this, you look it up, but here's the pod anti-affinity. So here's that hard requirement, and this is the web front end, and it's basically saying, don't repel ourselves, anti-affinity to ourselves at the host name level, and then here's our kind of preferred to the cache. And then the cache is doing the reverse. There's probably no point labeling the point, but you can see. And if we have a quick look at that example I showed you when I deployed it to my cluster, and we can see here, got cache and web, cache and web, cache and web, and each one is spread across. In this case, I use the host name across the host names. So I've got that behavior I expected. So as we've seen, there's quite a few options for having really fine-grained control over how we schedule. What if none of these suffice? You have what I call the nuclear option. So you can write a custom scheduler. So a scheduler that uses whatever custom logic you want to decide where the pods go. The schedule can be written in any language. There's an example on the web of somebody's written it in Bash, probably not production ready. It needs access to the API server, so that's important to bear in mind. And once you've got the scheduler, to use it is actually trivial. Now in our pod spec, we just say scheduler name, and we give it the name of the scheduler that's running in our cluster. So that's the deployment name. So that's scheduling, and I think you can see that there's quite a lot of power there. What if we want to extend Kubernetes or control it a bit more than the scheduling? There's other aspects we may want to take control of. An example of this might be we want to have control over the resources that are created. We may want to apply custom policies that say you must have, for example, every deployment must have some labels on it, which team owns it, or who to call if there's a problem, things like that. You may want to prevent certain resources from being created. The typical example here is load balancer services. People don't want load balancer services created because they've got some kind of ingress solution already. You may want to inject additional logic transparently into your resources. So rather than having everyone update their deployments, you may want to have some logic that adds maybe a sidecar container into a deployment whenever that resource is created. One of the ways you can do this is by using admission controllers. So admission controllers is essentially code which intercepts the API request before they're persisted and lets you do some things to them. There are 3 types of controllers. It can be validating controllers, it can be mutating controllers, and some controllers can do both. These controllers are enabled or disabled using the Kube API server. So this is a component within the control plane. If you went to Josh's talk yesterday, you would have seen him talk about the Kube API server and actually all of the control plane components. Problem with Kube API server is you have limited options when you're using a managed Kubernetes provider. So things like AKS, EKS, GKE, the control plane is managed for you. So you don't have many options in terms of controlling what runs. The other problem with admission controllers is they're compiled into the API server binary. So if you want your own admission controller, you might need to write some Go code, might need to fork Kubernetes, and then you may need to compile it and run it yourself. Good luck with anyone who wants to fork Kubernetes and run it themselves. There are a number of admission controllers already built in, and you have to find out with your specific cloud provider which ones are enabled. most of the cloud providers have enabled the sensible admission controllers. There are two I want to focus on, but before I do, let's have a look at the life cycle of an API request and see where these admission controllers come in. So I make a request, whether I'm using kube control, whether I'm using the UI, doesn't really matter. That hits the API server and the HTTP handler. So firstly, that goes through some authentication and authorization logic. Then it hits these mutating admission controllers. So these are the controllers which are changing the request. They might be modifying the existing request. They may be adding some additional resources to the requests. So for example, you might be asking for a one container. They may be adding another container into that pod. Once the mutation controllers run, we do some schema validation of the objects. Then the validating admission controllers run. And the validating ones run after the mutating, because otherwise you could mutate after you validated and become invalid. And finally, that request is persisted in etcd. And at this point, other custom controllers, other controllers kick in. So if this was a deployment, the deployment controller kicks in, detects that persisted change, and starts doing its thing. Within these two controllers, there's two special kind of controllers. And they've got fantastic names: mutating admission webhook controllers and validating admission webhook controllers. Try saying that 5 times in a row. So these special admission webhooks allow you, well, there's two of them. So the mutating one, as the name suggests, allows you to mutate resources. And the validating one allows you to block the creation of resources if you deem it to be invalid. These controllers, they invoke a HTTP callback. They're using web standard webhooks, industry standard. And the nice thing is this logic doesn't need to be compiled into the API server. In fact, the logic for these doesn't even need to be in the cluster. Logic for this can live outside of the cluster if you want. So let's have a quick look at how we can use these admission webhooks. This is where we pray to the demo gods. So when we want to set up an admission webhook, we need to define a validating webhook configuration. Can everyone see that? Is that big enough? I can't see the screen from there. Is that clear enough? Should we make it a bit bigger? So that's the resource kind. We have give it a name. The webhooks have to have another name, which is normally like your company URI. And then we say which rules we want to apply this webhook to. So in this case, I've said all API groups v1 on create of pods. And obviously, you've got quite a lot of flexibility there, what actions and on what resources you want this particular webhook to apply to. You've got failure policy. And that says, what do I do if there's an error running the webhook? So let's say there's the internet's down, for example, if there's an external connection. What do I do? The default, I think, is ignore, whereas this says fail. So this is going to ensure that if there's ever a technical issue, the webhook will still fail. So it means you can't deploy any pods. And finally, you can see the client config. And in this case, it's going to invoke an Azure function that's running in the cluster. Note the CA button is blank here because this is running on my Docker Kubernetes cluster. You would have to give a certificate if you were doing this for real. So let's have a look at my Azure Functions code. So this is a Node.js Azure function. And I've taken Kelsey Hightower's original version and made it work with Azure Functions. So the top bit's bog standard Azure Functions. We get the request body, and we grab the pod spec out of there. Here's the spec for the containers. And then we're going to look at the container image. What image are we using? If the image matches this particular image here, we're going to say that's the bad image. We're not allowed to use it. And we're going to send back a failure response. Otherwise, it's true, and we basically send allowed true, and we send that response back. So that's kind of 45-ish lines for controlling which image we run. So first of all, I need to ensure that I've deployed wrong. Just go to this window here. So I need to deploy that webhook configuration first, and let's have a look. Oh, oops, forgot the dash F. Everyone's watching, you see, and this is why. Okay, so now that configuration is created, actually let me show you. I've got two pod specs that I'm going to run. The first pod spec is using that image I'm not allowed to use, and I will show you afterwards that there's no smoke and mirrors. This is the one that I'm allowed to use because it's not the V1. Okay, so I should have an Azure Functions window open here, and I just need to connect to it again because this tends to time out. So this bit is a little bit unpredictable with the connection. We'll see the webhook should work. Hopefully we'll see the logs as well. But if not, we should still see the webhook effect. So just wait for that to connect. So I'm relying on the conference Wi-Fi. I'll give that another 2 seconds, and if it doesn't, I'll just show you the actual demo. Okay. I was thinking about it. We'll try it. It may not show the logs there, but let's try. So now if I apply, just remind myself what the file name was called. Hello world. Okay, apply -f. If I try the V1, I'll move that up a little bit. And we can see it says error from server, image not allowed, blah, blah, blah. Hello world is using a bad image. If I come over to the, okay, yeah, this logs don't always show, but it's actually invoking that Azure function. Just to show you that it is doing that, if I then try and apply the V2 image, which see that one is created. So find out, okay, get pods, oops, okay, pods, ignore the RabbitMQ, that's for another demo, but we can see the hello world is there. So I'm just gonna delete that for now because I don't want it there for the next one. So that was just a quick demo of the validating webhooks. I chose the validating webhooks because they're much easier to do. If you want mutating webhooks, they're a little bit harder because you need to be able to authenticate and authorize against the server. So the example I just showed you there was essentially using these webhooks as a policy, running some kind of policy. Please don't do that. There are better tools out there now for doing this. If my clicker has decided to die on me, my whole computer's died on me, I think. Come on. Yeah. If you want policy, if you want to control what can run, mandate certain things are present, then please have a look at the Open Policy Agent. This is using webhooks and admission webhooks in particular behind the scenes, but it's taking the abstraction a bit higher. So I wanted to show you how these things work, how that lower level infrastructure works, but you shouldn't need to do that unless you're trying to do something that OPA doesn't support. So that's kind of admission webhooks. What if you want to go even further? What if you want to extend the Kubernetes API? What if you want to build abstractions on top of existing Kubernetes resources? Or you want to create entirely new resources within Kubernetes? And you want to use kube control to manage these resources? You have a couple of options here. So one is you can create your own kube API server. It's called an extension server. That's a lot of work. You have to implement a whole API server yourself, and you have to have the persistence for it. Another option, and the one that I think most people have probably heard of, work with Kubernetes, is custom resource definitions, or CRDs. You also have custom controllers. And we'll talk about how those two fit together in a second. So talking about these custom resource definitions, this is a new resource type alongside the existing resources. So where we've got pods and deployments and services, you can create your own resource type. You can use kube control to manage those resources. So you can do kube control create, delete. We'll have a look at one of these in a second. And these custom resource definitions are persisted in the etcd cluster. Now, it's worth mentioning that if you create a custom resource definition without any custom controller, it's pretty useless. All you're essentially doing is doing some CRUD. And please don't use etcd as your data store for your own applications by creating custom resource definition. That's not a good idea. So how do we create a custom resource definition? Well, we create a resource kind called custom resource definition. We give it a name. We specify the version. And we have this scope. So the scope says, is this namespaced or cluster-wide scope? And then we give it some names. So we have the plural name, the singular name, the resource kind name, and then you have short names. So much like you have get PO for pods or get SVC for service, you can define your own custom name. Once you've created that custom resource definition, you can now create a custom resource. So much like you would have done with the pod, you can now create a custom resource. So this is my full resource. You can see it's got my API version I defined. Here's my kind. And now in the spec, I can put pretty much wherever I want. What I can do now is I can apply that, this little video, I can apply that custom resource. Now I can create an instance of a custom resource. So here's my kind of foo resource being created. And now I can do kube control, get foo. That was never built in originally, but there is. There's my foo object. I can use a shorthand. I can also delete that foo object. That's all I can do, though. That's it. But it's quite nice being able to use the same tooling, the same commands. So custom controllers can be used to change the behavior of resources. These can be existing resources. So if you want pods to behave in a different way, you can write a custom controller. More often than not, you'll see custom controllers paired with the custom resource definitions. So the custom resource definition is the state, if you like, and the controller is the logic that does the action, that does the magic. Custom controllers are often written in Go, but they don't have to be. And you often hear the term operator. And broadly speaking, an operator is the custom resource definition combined with the custom controller. If you want to write a custom operator, my first piece of advice is probably don't. Have a look if there's one already there. So there are loads of these out there now. This is one of the lists I've found. This is quite old now, but you can see it's quite small, but there's, for example, there's an AWS operator there. So this lets you provision AWS resources using kube control, which is quite cool. So you might say kube control create DynamoDB. It's quite cool. If you do want to write your own custom controller, there are a number of ways of doing this. There's a sample custom controller in the Kubernetes source code, which gives you an idea of how to do them. Another option is to use something like the operator framework. So this kind of bootstraps the building blocks of a operator and allows you to kind of get some of the boilerplate code out of the way. But as I said, this is not a task to be taken lightly. They're quite complicated, but obviously many people are creating operators either to abstract the kind of Kubernetes API, abstract their own business logic behind the Kubernetes API, or just because it's simpler than running lots of individual resources. So we're going to take a bit of a shift now. I'm talking a lot about scheduling and resources and extending. Crunching gear change now. I want to talk about scaling. There's almost no link to the prior section, except I do tie it back in, so bear with me. So we talk about auto-scaling within Kubernetes. I think most people have probably heard of the horizontal Pod Autoscaler. So this is the component which adds more pods into your cluster to deal with load. And there's a V2 Pod Autoscaler, which can actually use external metrics. So the V1 can only use the pod metrics, so it looks at CPU. I think we'll touch on this in a second. The V2 one's quite nice because they look at external metrics. There's another scaler called vertical pod autoscaler. And this scaler actually increases the amount of resources assigned to a pod when it needs it. So this is now vertical scaling, scaling up versus scaling out. Another option is in scaling is scaling the cluster itself. So the cluster autoscaler will see if there's pods waiting to be scheduled, which don't have, because of insufficient resources, can actually increase the amount of nodes in your cluster. Now this relies on where you're running this cluster. So if you're running in a cloud provider, it's going to kick into the cloud provider's infrastructure. The problem with cluster autoscaler is it's not particularly fast. It depends on the platform you're running on, but typically we're talking about minutes to add a new node to the cluster. Can you imagine what it's doing? It's spinning up another VM, then it's actually bringing that into the cluster, so it's doing all the bootstrapping it needs to do, kubelets and all that stuff. There's another option called the virtual kubelet / virtual node. So the virtual kubelet is an open source project that was originally created by some of the Microsoft team, and they donated it to the CNCF. And what this lets you do is lets you connect your Kubernetes cluster to some external compute provider. And we'll have another look at we'll have a look at this a little bit later. Before I dive into the kind of virtual node, I wanted to talk about autoscaling triggers. So what triggers autoscaling? And I've kind of touched on this already, but horizontal scaling uses the metrics from the pod, or the V1 did. So V1 looked at the CPU and memory usage of your pod and determined if it needed to scale out. The V2 is really nice because now it can use metrics from external sources. So for example, you can scale up based on how many items you've got in a queue, for example, which is pretty cool. The VPA, no surprise really, it looks at the CPU and memory usage of the pod. And then as I touched on already, the cluster autoscaler says, are there any pods waiting to be scheduled because there's not enough resources? That's the trigger. One of the issues that Kubernetes has had, and the very last release has kind of ruined this bit of the talk for me, Kubernetes wasn't able to auto-scale deployments down to 0. So why would you care about that? Well, if you're running a microservices architecture and you have message handlers which are responding to messages on a queue, and maybe these messages are only fired once a week, once a month. Previously, you would have to have a message handler sitting there waiting for that message the whole time, because the autoscaler can only scale down to 1 as a minimum number. You might be running Azure Functions or function-style applications where you're responding to an event and then handlers kick in. And up until 1.15, this wasn't possible. In 1.15, they added the ability to do scaling to 0, but it's very early alpha feature and it's behind a feature gate. In 1.16, I believe the feature gate's been removed, but it's still unclear at the moment whether this is going to behave exactly as we anticipate, because when Kubernetes didn't have this feature, the KEDA or KEDA was introduced. So KEDA is a Kubernetes event-driven autoscaler, and it was an open source project that was led by Microsoft and Red Hat. And essentially, it allows you to auto-scale deployments to 0 instances, and also scale up from 0 instances to n number of instances on demand. The way that works is, essentially, KEDA acts as a metric server and also responds to events from external sources. And combined together, what it allows you to do is say when there's an event. So for example, if it's looking at a queue, when there's n number of messages on a queue, then start scaling up the deployment. So much like the HPA is doing, except critically go down to 0. So KEDA has a number of scalers and event sources at the moment. So it will allow you to react to AWS events on CloudWatch, Service Bus, GCP, Kafka, tons of these, and there were many others in development as well. And I'll show you a demo, if time allows, on the RabbitMQ one. So I talked about that virtual node before. I said we have this virtual node and virtual kubelet. So let me clarify the terminology, just in case it's confusing. So virtual kubelet is the underlying technology, and the implementation is a virtual node. And what virtual node does is when you install it into your Kubernetes cluster, it gives you another node. So here I've got 3 existing nodes in my cluster, and these could be bare metal or virtual machines. When I add the virtual node, I get a 4th node. It looks like any other node. It implements most of the node and pod functionality I would expect, except this virtual node is being powered by an external compute provider. So what this lets me do is treat it like another node, use kube control as I normally would, except now those pods are running somewhere else. Where is that somewhere else? There are a number of implementations. So Azure Container Instances is one of these. We have Fargate, Nomad, various others. I'm going to show you a demo with ACI. So just briefly, Azure Container Instances are the kind of serverless container offering on Kubernetes, on Azure. So just to get the buzzwords in there as well. So essentially, you don't need to provision any architecture. You just give ACI your container and tell it to run it. You pay per second for the running container. And this is really good for testing images, for running short-lived containers, and now with the virtual node, maybe for handling sudden spikes in traffic. So for example, I've got a cluster, and I've got 3 nodes in that cluster, and I've got the virtual node installed as well. I get a sudden spike in traffic, and my existing nodes are running hot. I'm running out of space, running out of capacity. I could scale my cluster at this point, but that might take 2, 3, 4 minutes. If this is an e-commerce site, I'm losing customers at this point. I'm losing sales. With the virtual node, what can happen is those additional pods to handle the load can be spun up onto ACI. We're now handling those customers' requests. And when the load goes away, those containers go away. Oops, those containers go away, and we stop paying for that additional compute. So in AKS, this is just an option you enable. For other cloud providers, you can get hold of the Virtual Kubelet project and just install it yourself. If you wanted to, you could actually have, for example, a AWS cluster, EKS cluster, spanning out into ACI. I don't know why you would, but you could. Be mindful that you'd have to give some service principal credentials, things like that, to the actual component, and that's not something you necessarily want to do. So I've got about 12 minutes, so hopefully I can get some demos done in that time and leave some time for questions. So let's have a look at a CADA demo first, I think. So in my cluster at the moment, if I do kget pods, you can see I've got RabbitMQ. So I've got RabbitMQ queue installed. And what I'm going to be deploying is a small Go application, 2 components, one that's reading from the queue, one that's writing to the queue. So in fact, I've already deployed the one that's reading from the queue. So if I do kget deployments, we can see we have this consumer, and it's sitting there with 0 instances. So there's no pods, but I've got the consumer, the one that's waiting for messages off the queue, sitting there. It's not taking any resources because there's no pods running. Let me quickly show you the YAML file. So here's the consumer. So the top bit's just fairly standard deployment. The magic is brought about by this custom resource definition. This custom resource definition is saying that I want to scale the RabbitMQ deployment, and I have some polling intervals here for how quickly I poll for it, how quickly I cool down, how many replicas I run, and then here's the trigger. So the trigger is listening to the RabbitMQ, and it's looking for a queue depth going above 5. Okay, so this custom resource definition, this scaled object was added by CADA. So you can see the API version is in the CADA namespace. So that's the magic, really. The publisher is just the Kubernetes job, which is just going to run the Go binary, and it's going to dump a load of messages into the queue. The consumer is waiting, I think, about a second between each. Each consumer's pausing for about half a second or a second, I think, just to kind of demonstrate the effect. So now if I come over to here, and if I apply the, if I can type, it's the publisher. So now that job is running. So now it's spitting pods. It's adding. So this is the publisher running. If I now do get pods again, see that's finished. So what we should start seeing, this demo isn't failing. There we are. So we can see now there's a consumer spun up. So it was 0 instances. We now have 1 consumer. Now, because I'm on a Windows terminal, I can't do the watch command that refreshes nicely. So I'm just going to do that. We can see now we have a lot more. If I keep on doing that periodically, we'll see. If I just do kget deployments, we'll see we're up to 5 of 8. And actually, as I showed you in the config, it'll scale up to 30 instances. So we're up to 16. See that? This should only take another 30 seconds or so. So we can see loads of consumers. Each of them is reading off that queue. And what we should start seeing very soon is once they're finished and there's nothing left in the queue. So we're up to the max now. We're up to the 30. I'll give this another 30 seconds or so. If not, we can come back to it. Oh yeah, that was that. That's how quick that was. So we can see in the time it took me to say I'll give it 30 seconds, we went from 30, it scaled all the way back down to 0. So if I now do kget pods, oops, we'll see that's the RabbitMQ, oops, and that's that publisher component. That was just the job, so it's completed. And we've scaled back down to 0 again. So that's quite cool. The next demo is the virtual node demo, and this one does rely on a lot of fiddling with Windows and having a good internet connection. So I'm going to rely on a video for this one. Hopefully people can see the video. If not, feel free to move a little bit closer. So here in my cluster, I've got the virtual node applied. And I should have said, actually, the virtual node supports, there's a Windows and a Linux virtual node you can have. So this is a Linux one. So I've got 3 existing nodes in my cluster. And I've got the virtual node. If I have a look at that virtual node, if I describe it, what we'll see is that I typed really slowly. What we'll see is that it's got some labels. And one of the labels is type equals virtual kubelet. More importantly, it's got a taint on it. So the taint says, don't schedule. Because I wouldn't want to schedule pods. I'm just going to pause that a second. I don't want to schedule pods on that virtual node because I'm going to be paying for ACI instances. If I've got existing capacity, I don't want to deploy anything to it. So I taint it. Incidentally, while I've got the video paused, notice the capacity of the cluster. It's got 800 CPUs and 4 terabytes. This is the virtual node, 4 terabytes of memory. This can be whatever number it wants to be. This is your credit card size, basically. So, okay, so that's the virtual node. So let's have a look at the deployments. So this is a web kind of e-commerce site. Few components running, but the one we're really interested in is the online store. Let's have a look at where they're all running. You can see they're all running on the actual AKS nodes, and that's the one we're interested in. That's our e-commerce site, and recklessly, we've only got 1 instance of our e-commerce site running because we like living on the edge. If I have a look at that pod, we can see that I think I was struggling to find the relevant section. There we are. So you can see that it tolerates the taint. So it's tolerating the ACI taint. So it's saying I'm allowed to run on that virtual node. So why isn't it already running on the virtual node? Because we've set an anti-affinity. So we've said, prefer not to run on that virtual node, but you are allowed to run on it. So it's now combining those two effects, which means that we're not using it unless we need to. So you can see they're not in virtual node. So prefer not to run, but you do tolerate it otherwise. So here's that e-commerce site. And you can do various things. You can add things to the cart. I'm conscious of time, I might just jump a little bit. So what we're going to do is we're going to split the windows in a second, and we're going to bring up App Insights, which is showing the metrics from that site. So we can see I've got essentially 1 request per second coming in, and request duration is essentially 0 milliseconds. In this bottom pane, in the Cloud Shell, I'm going to run a load test. I'm running a component called Hey, which is a really nice load testing tool, very easy to use. And if you keep an eye on the top right window, you see suddenly there's a spike in requests. So we're now going to 200 requests per second, and our request duration has jumped up a little bit. It's jumped up to 500 milliseconds. On the left-hand side, on the cube control window, what we'll do now is we'll have a look at the pods we're running. So remember there was 1 pod running before. If I do get pods, we can see there's a lot more of the online store pods running. Probably more interestingly, let's have a look where they're running. So if I run that with the O wide, and incidentally, if you now look at the request duration, you see now it's dropped down again. So even the load is actually going up at this point, but the request duration is now dropping down. So if I now have a look at where those pods are running, you can see they're running on the virtual node. So at this point, I'm paying for them. Per second, I'm paying for those. But hopefully, people are buying really expensive Surface devices, are making decent margins on them. This is all real time at this point. This was real time. That scaled up in real time. I didn't fudge the video. What we'll do is, as you can see, the request rate is going up and up and up, and actually the duration is very good. It's 0 or just above. What we can do now is, if I kill that load test, we'll see the request rate drops to 0. Now this takes about 90 seconds, and I didn't want to have a video running for 90 seconds and me have to fill. So I did edit the video at this point, but 90 seconds later, when we do get pods, we can see we're back down to that existing app pod. The virtual node stuff is all gone. So we've stopped paying for it now. We're back down to the existing number. So that was the virtual node. The video continues just to show it again, just how quickly it is, but I think given the time, I'll stop it there. So that was the last demo. And let's just wrap up. So what did you just see? You saw that the virtual node was tainted to prevent pods from being scheduled onto it accidentally. And that e-commerce shop deployment was configured to tolerate the virtual node, but also have an anti-affinity to minimize the usage of the virtual node. And that allowed us, when we scaled up, to use the virtual node, pay the per second billing on the ACI containers, and once we were finished, we're done. So just to wrap up, as we've hopefully seen, there's lots of really powerful constructs within Kubernetes to control pod scheduling. And the admission webhooks give us quite a lot of power in terms of customizing what resources are created. If you want ultimate control and extensibility, you need to have custom controllers with custom resources. And finally, with something like the virtual node, and I didn't show it here, but you could combine the KDA scaling with the virtual node, and you have scaling to 0 and virtual node, which means you are having serverless clusters. You're not paying for, on Azure and Google, you don't pay for the control plane. If you have serverless nodes, you don't pay for the nodes unless you're running some workloads. If you have KDA scheduling, you have 0 pods unless there's something happening. So you have true serverless Kubernetes clusters. If you want to learn more, that virtual node scaling demo is on that GitHub repo there. In the synopsis of this talk, I mentioned about service meshes, but there's a talk tomorrow about service meshes, so I didn't cover that. I do talk about service meshes. I did a talk here last year, actually, which is a higher level kind of microservices talk, and I cover service meshes in there. And if you want to learn more about lots of these cloud-native technologies, I highly recommend Katacoda. And with that, I think I'm literally 11 seconds over. So I'll say thank you very much. The slides are available at that link there. Happy to take questions outside. Otherwise, thank you so much.